Hello, can you hear me?
Yes, we hear you.
Yes, we hear you.
Excellent. So, hello everyone, my name is Andrachum. I am from Czech Technical University in Prague, and I'm actually from Prague. I hope we are all doing well these days, and I'll be speaking about traditional approaches to RANSAC. Just to quickly recap the RANSAC algorithm, you have a set of data points, which in 2-view geometry is correspondences. You have a function that computes model parameters given a set of correspondences, and you also need a cost function that basically tells you how far a data point is from the model you have. And the output is the parameters of the best model that fits the data with the highest cost function. And the algorithm goes, it repeats 2 steps until the probability of finding better solution is below certain threshold. In first step, you generate hypotheses by selecting a random sample, which is the minimal size, so that you are able to estimate finite number of samples, so for a finite number of models. So for example, if you are estimating homography, from 4 correspondences you have a single homography, whereas if you are trying to estimate fundamental matrix, you have from 7 point, using 7-point algorithm, you have 1 to 3 fundamental matrices. And you compute the parameters, and for each of the models, you compute the cost. And if the cost is the best so far, you just store the cost and you also store the parameters so that you have something to output. So in this talk, I'll be speaking about a few improvements to the original RANSAC so that we don't have to sample uniformly. We can do something better. We can check for additional constraints, which might speed up the process by omitting some of the verification. You can explicitly try to minimize the number of verifications that you do, the number of cost computations. And I'll speak about certain problems that are introduced by degeneracy, degenerate configurations, and also about how to improve the precision and stability of RANSAC. So in the talk, I'll be speaking more about the ideas rather than about exact ways how to implement these things. And this talk is in no way touching all the improvements of RANSAC. It goes mostly through improvements that were implemented in USAC, which is a modular software where you can pick what kind of sampling, optimization, and random verification or whatever you want to use, and most of this stuff is implemented there. So let me start with non-uniform sampling, and let's start with local sampling, which is based on the observation that inliers often lie on densely populated manifolds. So if we look at those 2 highlighted points, one being inlier to the line and the other outlier, and if you look at their neighborhoods, you can see that in the neighborhood of the inlier, there's significantly more data points than in the neighborhood of the outlier. So we can take advantage of this by selecting first 1 point at random and then drawing the rest of the sample from its neighborhood. This increases the chances of hitting all inlier sample. On the other hand, such samples are typically so one has to take care of that. And depending on the type of neighborhood, there is a number of methods that were introduced, starting from knapsack, groupsack, MaxSac++, which Daniel will be speaking about in next, many other that were published. I want to show one thing. I want to show that this idea has been has been here for a while. So in 1997, Schmidt and Moore proposed some pre-verification of a tentative match. So if you have two features in two images that are lookalike, can we somewhat estimate whether these are going to be good matches or whether these are going to be outliers? So, and they suggest to have a look at the neighborhood, local neighborhood of those features. And if in the neighborhood of those features there are features that are also matching, then this original feature that we are interested in is quite likely to be an inlier. That is, there are other inliers, that there are other points on the manifold locally. If there is nothing, then it's likely that this is not the correct match and it can be discarded. And this procedure is actually quite often used as a pre-filter trying to reduce the number of outliers in your data. So next, I'll be speaking about progressive sample of consensus, which takes another assumption, and that is that we have some measure of quality of our data, of our correspondences. And in computer vision problems, this is very often the case, because the way how you form the tentative correspondences is that you do some feature matching based on descriptor distance or some first to second nearest neighbor ratio, and you threshold this quality to get inliers or to get tentative correspondences, and those that are worse than certain threshold, you just drop them. So you have such a quality, so why not to try to use it in the sampling process? It might seem useful to try to estimate actual probability of correctness of the match, but this might be tricky, and we will avoid that. We will just go for simple comparison that certain tentative correspondences are better than others. So we will quality, and we will order all the correspondences according to the quality. This would go that this red one would go in front of this blue one. And how do we use this to improve RANSAC? So the idea is to evaluate better samples than worse samples, and the quality of samples we can define by the quality of the worst correspondence in the sample. And the procedure would be as follows. You first draw all samples, the maximum number of samples you want to evaluate, and then order those samples by the quality of the sample, so that better samples go first and progressively worse and worse samples. And then you just evaluate those samples in this particular order. This is this advantage that better samples are evaluated first, but if the quality is not giving you the right thing, then in the end, you evaluate exactly the same samples as a standard RANSAC would evaluate, so you are not losing anything. This procedure, however, is rather inefficient, so on the next slide, I will show how to draw the samples efficiently. We will start from the best M correspondences, and basically we will draw the samples based on the quality. So we will be improving the quality of the sample, which is the worst correspondence in the sample, and we will estimate the expected number of samples with this given quality, and we will construct the samples so that the worst correspondence is the one given by the quality, and the rest of the sample is drawn uniformly from better correspondences. And we will draw this for given quality, and then we move to another one. So this is doing the same thing as on previous slide, just more efficiently. So this was how we can exploit the quality in RANSAC in the sampling stage. But perhaps we might exploit it even in determination criteria. Because how the tentative correspondences are created? You do pairwise matching, and then you threshold the quality somewhere, and you take tentative correspondences and you discard the rest. And we said previously that the number of samples that is drawn in RANSAC depends on the fraction of inliers. So would it be possible to choose the threshold on the fly so that the fraction of inliers is actually maximized on the top set of the correspondences so that we can terminate earlier? This is very tempting, but it has certain problems. For example, small sets of tentative correspondences will have very high fractions of inliers. So for example, if you are drawing 7 correspondences and you took only first 7 correspondences, then you would have 100% inline ratio, which is obviously not the thing that you want to do. So you want to also introduce a thing that will prevent this, and you would like to select the threshold so that the number of inliers is non-random in your set that you are selected, that you need the process. And the other problem with this is that the ordering often introduces bias. For example, if you have frontoparallel plane, the matches on this plane will be are likely to be better than matches that where there is a significant change of viewing angle. And so this type of stopping criteria may suffer from stopping too early based on degenerate configurations. So this has to be considered when using this type of stopping criteria. So an example, there is a image pair, there is a motion in the scene, so there are actually 2 models. So in total, there are 783 correspondences, and the background correspondences have 79% of those tentative correspondences. So both PROSAC and RANSAC find easily all the correspondences. PROSAC does it in a single sample, and RANSAC, since the inline ratio is high, takes 15 samples. And here the blue circle length that was selected by RANSAC. Then if we exclude inliers to the background model and we run the RANSAC again, then we have only 31% of inliers. And suddenly RANSAC needs 10,000 samples, whereas PROSAC is happy only with 18%, with 18 samples. And again, the blue circle shows the stopping criteria, stopping length. There is actually a shorter sequence of tentative correspondences that would lead to faster stopping, but this turns out to be too small, so that the number of inliers within this sequence can be random. So that was it for PROSAC. Now I'll move on with locally optimized RANSAC. So just to quickly recap, it was said that RANSAC, you select a sample at random, you fit the model, you find inliers, and you repeat this until you hit an all inlier sample, and then you extract all the inliers. You just need to make sure that there is no better model in the data and everything is done. However, this sample is also an all inlier sample. However, the model does not recover all the inliers. So you have a smaller number of inliers, and the RANSAC tends to run longer, needs more samples to stop based on this number of inliers. However, in the end, you may not observe this, because if you do, for example, least square fit to all your inliers, you will get pretty decent model. So the idea here would be, can we actually do something like least squares fit or any local optimization inside the RANSAC, so that we actually discover all the inliers, and we can terminate the RANSAC earlier. So if we find so far the best model from the sampling, you can actually run local optimization on this model to find all the inliers and to have better idea what fraction of inliers is in the data. So how often do we execute such an optimization? How often we observe so far the best sample? And it turns out that this happens logarithmically with the number of samples. So it's not that many times throughout the execution of RANSAC, and the local optimization can be relatively complex compared to just constructing the model from a sample. And there were a number of local optimization steps proposed, starting from least squares fit, iteratively weighted least squares, in RANSAC, where basically you resample correspondences, and also using some more constraints such as locality, so that data points that are close to each other should be labeled similarly in fashion of GraphCut, and Daniel in the next talk will be speaking more about this. So let's have a look at the stability of RANSAC and LO RANSAC. So what we have here is two plots. One for we've executed the estimation 10,000 times, and every time we get a different result because it's a randomized algorithm. So for each correspondence, we have recorded in the top plot how many times it was labeled as, or output as inlier. And the optimal shape of this plot is that all inliers are always labeled, all outliers are always labeled as outliers, so that the blue area is actually rectangle. The second plot shows, so over those 10,000 executions, each data point was labeled as inlier a certain amount of times. So this is on the x-axis, and how many correspondences were labeled this many times is on the second axis, is on the y-axis. So ideally, this would be just two bars, one for outliers on the left-hand side, that they have probability 0 of being labeled as inlier, and one on the other side, all inliers have probability 1 being labeled as outliers over the executions. So here, if you compare RANSAC to locally optimized RANSAC, you can see that the locally optimized RANSAC is actually for this pair of images showing optimal. Here's another example. Again, RANSAC, unstable LO RANSAC. The same for epipolar geometry. The variation is slightly higher there. So this is the way how locally optimized RANSAC basically stabilizes the results and can get good results even from not so good original hypotheses. So this can be exploited even further by using imprecise or approximate models, and then in local optimization trying to estimate the correct model. So why is this interesting? Because you can get enormous speed up, because you should be able to reduce the sample size by this way. So one of the methods I want to mention is, instead of degrading features feature matches to simple point-to-point matches, you can actually estimate something that is called local affine frame, so that each region-to-region correspondence gives you 3 point-to-point correspondences. And hence, you can estimate, for example, epipolar geometry instead of 7 points, 7-point correspondences from 3 local affine frame correspondences. The problem with this is that the points are close to each other, so the models are of lower precision. However, if your local optimization is able to fix that, everything will work. Another approach is that you can not only use more information from a single match, but you can also use some approximate model. So instead of estimating exactly epipolar geometry, you can estimate approximate model, for example, approximate affine epipolar geometry, for which you need only 2 local affine frame correspondences. And in the local optimization step, you will take inliers to this model and you will try to refine the full model. So if you have a look at the table, which shows the number of samples that you need for different inlier ratios, which are shown here, and the different model complexity. So this would be a model where you need to draw samples of 2 correspondences, for example, line fitting, homography 4 correspondences, epipolar geometry 7 correspondences. Then the previous thing, if you, instead of sampling 7-point correspondences, you sample 2 local affine frames, and then use local optimization to refine the model. Then for low inlier ratios, the speed up is enormous because both approaches have the same number of inliers. But instead of sampling 7 tuples, you are sampling just pairs. So the potential gain here is large. So now let me move to degenerate configurations. I will first explain what these are, what kind of problems do we have with degenerate configurations, and how can we deal with them. So far we were interested in data with outliers, and now we are interested in degenerate data with outliers, or the degenerate part is the chunk of the points in the middle. And the problem with the degenerate configuration is that there is infinite number of models that are passing through this degenerate configuration, and all of those models are consistent with all the points in the degenerate configuration. So you can have, if you sample your sample and estimate a model from a sample that contains say degenerate configuration and outliers, you can have a model with high number of inliers. However, this model can be completely wrong. So this is some toy example. In 2U geometry estimation, the typical degenerate configuration is a dominant plane. So if you have a huge plane in the scene that has lots of points, such as this one, where there is majority of points lies on a plane, then there are some points that lie close to the plane, and there are only a few points that lie off the plane, and these are located on the lamppost. And if you run standard RANSAC with 95% confidence that you find the best solution, actually only 17% of the executions return as inliers the correspondences on the lamppost. So how to deal with the degenerate configurations? Well, when you sample a model that has a high number of inliers, you can take those inliers and you can run another RANSAC for a model that would model your degenerate configuration, and this way you can find the degenerate configuration. And this is actually what QDEC-SAC is doing. I'll also speak about another approach, which is called the RANSAC, and it has one assumption that if you take a all outlier sample as here, then it is very unlikely that such a sample would lead to a model that your degenerate configuration. It seems on this toy example that it quite often, but typically in high dimensional data, this is really unlikely to happen unless there is some special condition, and I'll mention this later on. So we assume that if we sample a model that has a high number of inliers because of the degenerate configuration, we assume that the sample spans the degenerate configuration. And then in such a case, you don't have to run a new RANSAC. You can analyze the sample directly. And this is deterministic and typically is way faster than running another RANSAC on the inliers. So it turns out that in two-view geometry, there's a really nice algebra related to this. So if you have a dominant plane and you are using, and you would like to estimate epipolar geometry by drawing 7 correspondences, it is likely that you will draw a high number of correspondences into the sample from the dominant plane. So if you draw 7 or 6 correspondences and use a 7-point algorithm, then you will get, this is the degenerate sample, at a whole family of fundamental matrices. So this can be easily detected and this is not a problem. However, we've shown that 5 coplanar points and then 2 points, 2-point correspondences of the plane, which can be even outliers. Then the 7-point algorithm returns a model that is consistent, at least one of the models is consistent with the whole homography, so with the whole dominant plane, and therefore such a model would have large support. So what does it mean? Here is a scene where there is dominant plane, lots of features on the dominant plane, and I have selected 4, manually picked 4 correspondences, 2 on the plane and 2 off the plane. And on the first image pair, you can see a homography that is actually the correct model, and you can see that all 4 correspondences are consistent with this homography. In all the other examples, you have different homography, different fundamental matrices. All of them are consistent with the whole ground plane, but none of them is consistent with the points of the plane. So only the first one is the correct geometry, incorrect, but the number of inliers is almost the same, so it might be difficult to determine between those unless you explicitly go for detection of degenerate configurations. So how the RANSAC would work in estimation. You draw samples of 7 correspondences, you get 1, 2, 3 fundamental matrices, then you test the sample, which is quite efficient. You need to perform just, I think, 5 tests on 4 tuples. And when you detect homography, then you take this homography and you use plane and parallax to recover the inliers that are off the plane. The plane and parallax algorithm is way faster than anything else because it only needs 2 correspondences. And this way you can get actually decent and stable results. So if you compare approach that takes care of degenerate configurations with standard RANSAC, you can see that the RANSAC is fairly stable, whereas for RANSAC, basically anything can end up as an inlier. So degenerate configurations are not only problematic, it actually, everything that I've said so far can be taken in, can be used in our advantage by drawing non-minimum samples. So let's explain this on an example of fitting a line in through or more dimensional data points. So standard approach would be you sample 2 points, you fit line for inliers. In this approach, instead of drawing 2 points, you draw 3 points, you fit a plane, and if the plane has enough or high number of inliers, you check the 3 lines defined by the 3 points, whether one of those lines is the line that you are looking for. So this is basically a test for degeneracy of the plane. So what is the advantage of this? If you are sampling 2 points, you need both of them to lie on the line in order to find the line. If you are sampling 3 points, then if at least 2 points out of those 3 are on the line, then the whole system with the line. So the probability that you take 2 out of 3 is much higher than that you will take 2 out of 2. The problem is if all the points occupy in your space only a plane. So in this case, any sample, even 3 points that do not lie on your line, if you model a plane, it will be always the same plane where all the points lie. And this would be the example where all inlier sample actually randomly hits the degenerate configuration. So this is where this approach will not bring you anything. You'll be just sampling triplets of lines instead of a single line. So non-minimal samples for homography estimation. So similarly as in previous case, we will try to find a lower dimensional model by estimating higher dimensional model. So instead of drawing 4 correspondences need to be correct in order to estimate correct homography, we will be drawing 7 tuples of correspondences, and if at least 5 layers, then we will cover the homography as a degenerate configuration of this epipolar geometry. And if we plot the ratio of those 2 probabilities, you can see that for almost all inlier ratios over something like 7.2%, it is actually faster to try to estimate epipolar geometry and then detect the degenerate configuration as a plane rather than sampling 4 points. When you have something like 40% of inliers, it's more than 3.5 times faster. So that was degenerate configurations. The last 2 bits I want to speak about will deal with how to avoid or minimize the number of verifications. So first is checking the samples. So there might be certain models that there are constraints that do not reduce the number of points that you need to sample, but reduce the size of the models. So it was difficult to come up with the toy example, but for example, if you're fitting a line, if you're trying to find a line segment of fixed length, you still need 2 points as if you were fitting a line, but the line segment is another constraint. So what would be the possible approaches how to handle this? Well, you can try to sample only hypotheses or models that are satisfying those constraints, but this might be difficult to do or even intractable. You can also choose to ignore it. And this typically works okay because models that do not satisfy those additional constraints typically have small support and will be rejected anyway. Or you can try to apply those constraints on the sample. And if you can reject the hypothesis based directly on the sample, you can save on the verification. So for example, if you sample 2 points and we are trying to find a line segment of fixed length, so if those 2 points are further away than the length, they clearly do not lie segment of fixed line of this particular length. So in two-view geometry estimation, the constraint are the oriented constraints that come from the fact that cameras do not see on whole rays, they only see on half rays that go from camera to scene. So they do not see points behind the cameras. And this topic was the hot topic like 30-20 years ago, and lots of papers were written on this. So how do we apply those constraints on two-view geometry estimation? For homography, it is simple. You only the homography needs to preserve convexity. So you compute A determinants, you do 4 comparisons, and you can decide whether the sample can be homography that is a real-world homography, or whether you can reject it. And you can do this. You can perform this type of test even without computing the homography matrix, which can save you additional time. With epipolar geometry, it's slightly different. So there are oriented constraints that basically say that the epipolar half line that is given by the fundamental matrix and a point in one image should be the same half line that goes from to the point that is to the corresponding point that is measured in the other image. And if you take this constraint and do some algebraic tricks, you will get to the standard unoriented constraint. So the oriented constraint is stricter than the unoriented. And what you can do, you can estimate your fundamental matrix as usual using the standard constraint. Then you can take the 7 correspondences that were used to estimate in the fundamental matrix and check whether the oriented constraint holds for all of them, which is very efficient, only a few floating point operations. And this way you can discard up to almost half of the models depending on the type of the geometry. So if it's short baseline, then it's less, and if line, you can discard more models. And finally, we are getting to randomized verification, which is we would like to avoid verifying correspondences for models that after verifying a few correspondences, we know it is hopeless. So in order to do this, we have to go a little bit into time complexity analysis of RANSAC. So we know that the number of samples grows exponentially with the model, success of the model, and also depends on the inlier ratio. But what we were neglecting is the number of correspondences. So if you have many correspondences, so for example, if you have some volumetric data and many correspondences, then every single hypothesis is verified. And this also takes some time. And the more correspondences we have, the more time it takes. So the time of RANSAC can be divided in time spent in hypothesis generation and in the verification. And it consists of the average number of models that you have per sample. So for example, this is 1 to 3 for epipolar geometry. I believe the average is something like 2.3. And the number of points, because for every model, you are verifying all the points. So the overall time spent in K samples is the formula here. So now we can introduce some pre-verification tests, which is we draw few correspondences at random, we verify them, and if it looks that this hypothesis is unlikely to be a good one, we can reject it. Otherwise, we verify everything. So this way, we can reduce the number of verifications per model. So the overall time will decrease. Let's have a look what are the possible errors that we can do. So false positive of this test is that we do not reject incorrect model. This doesn't make any harm because it only decreases the efficiency. So if we verify a model that is no good, then we spend more time on verification, but no harm is done. False negatives, it's problem, because if we reject correct model with certain probability, then it means that we are decreasing confidence in the solution, because the confidence in the solution is basically probability that we have not sampled a good model. But here it can happen that we do sample a good model, but we reject it. So therefore, in order to keep the same guarantees as a RANSAC has within K samples, we need to increase the number of samples with this pre-verification test by 1/1 minus the probability of rejecting a good model. So in this case, to get the same guarantees as a RANSAC that would draw K samples, the time complexity of RANSAC with pre-verification would be like this. And what we are looking for is techniques that would give you the same guarantees as RANSAC, but would run faster. So the first, to my knowledge, the first idea of randomized verification is the TDD test, which is very simple. You take small number of points, D points, and you verify them. And if all of them are consistent with the model, you verify the rest. And if consistent, you just drop the sample and go and take another run. So it turns out that for the most problem ratios, the optimal value for D is 1, so T11 test, which means you hypothesize your model, you take one correspondence. If it is consistent, you verify everything. If it's not consistent, the sample. So here is some synthetic experiment on epipolar geometry estimation, 1500 correspondences, 40% of inliers, and results averaged over 30 repetitions. And for standard RANSAC, which is the first line, you have the smallest number of samples, but with each sample, you verify all the correspondences. If you do T11 test, the number of samples increases, but the number of tests is significantly reduced, because for most of the samples you verify only one correspondence. And if you go for T22 test, then the number of samples increases even more, because you are rejecting more and more samples. But even with the rejected sample, you do at least 2 tests, so the number of tests increases over T11 test. So this is just the intuition why T11 test is the most efficient. Next method that I want to speak about is the bailout test, which is more sophisticated. And it goes through all the correspondences and tries to verify one by one. And after each verification, it tries to decide whether what you've seen so far has a chance to be the best model, or whether you should reject it. To compute this probability is intractable. So instead, you approximate the expected number of inliers of a good model by a normal distribution, and then you base your test on some quantile of this normal distribution, and if you fall below this quantile, you discard the hypothesis. And of the quantile is basically a parameter of the method, saying how strict this is. Finally, I would like to speak about USAC, which is optimal randomized verification for RANSAC. And this is based on sequential decision making, which basically is a way where you are trying to minimize the number of observations before you reject or accept a hypothesis that gives you a bound on false positive and false negatives. So with sequential decision making, after each observation, you can either reject the hypothesis of the model or accept, or you may decide to take another observation because you cannot do any of the previous decisions in order to satisfy the bounds on false positives and false negatives. What does it mean in randomized verification? If you reject the hypothesis, you discard the model, and you proceed with another sample. The decision to accept the model is never taken, because when you accept the model, you say, okay, this is a good model. I need to know the number of inliers, so verify all the correspondences, which you can as well do sequentially by the last decision. So, which means verify the data. So you either reject the model or you go on with the verification. And Walt in his book provides a method to do this optimally, which is based on sequentially probability ratio test, and also provides the guarantees. And what is important here, that it has a single and you can and A gives you, the choice of A gives you the probability of rejecting a good model, which is 1 over A, and also gives you number or expected number, which is C log A, where C is some constant. So if you then write the time of RANSAC with the Walt test, you can see that it is a function of this parameter A, where you can basically find optimal value of A by setting the derivative to 0 and finding a solution. So this means that for your particular problem, you are able to find a parameter of the optimal test that is optimal, so that your randomized verification is optimal. So just to see how it compares, synthetic experiment, epipolar geometry estimation, 30% of inliers, and we were varying the number of correspondences. And we can see that for a small number of correspondences, the verification doesn't play important role, but for a large number of correspondences, large N, we can see that the standard RANSAC that every time verifies everything, basically the time takes off. So if we have a look at the same numbers, just rescale it and drop RANSAC, you can see that TDD test, T11 test, even though very simple, is doing reasonably well, but not as good as the other tests. And if you drop that one as well, then you can see that the optimal randomized verification is doing the best. Here we can see the black column is theoretic estimation, where we know exactly what is the ratio of inliers. The yellow bar is the realistic implementation, where the number of inliers is estimated from so far the best sample, and bailout test. I would like in this section to mention 2 more approaches. The first one is called latent RANSAC, which basically go into the verification step unless you have randomly generated similar model twice. So you generate a hypothesis, then you parameterize it in latent space, where this parameterization, if you have 2 similar geometries, 2 similar models, those 2 parameterizations are close. Then you hash this parameterization into some hash table, and if you observe collision, then you go into verification, and if you do not observe a collision, then you go and generate a new sample. This way, you can actually avoid verification until very late. Interestingly, this idea is also here for quite some time. So in 1990, it was used to detect curves, and the method is called randomized half transform. The problem with this approach lies in this parameterization in latent space. Typically, for some it is possible and relatively easy to find meaningful parameterization so that two similar models would be close. However, for high-dimensional models such as fundamental matrix or even for homography, this might be problematic and may not generalize to all possible situations. And the final I would like to speak about is slightly different from previous tasks. So in previous tasks, we were interested in certain confidence in the solution. Here, this is designed for real-time systems where you have where you need to estimate the best model you can within a fixed time budget. So if you are given this time budget, what you can do, you can compute how many hypotheses you are able to generate and verify, and then go and generate Y-bound one and verify and pick the best one. So the idea here is that the hypotheses that are better are likely to be better on a fraction of the data as well. So preemptive RANSAC, proposed by David Nister, generates higher number of hypotheses, but verifies only a small fraction of the observations. And you have some estimate how good each of the hypotheses is. So you drop all those that have small number of inliers, and you keep only those that have higher number of inliers. So say half, and you continue verifying only those more promising hypotheses. You have more verifications, you have better estimate of which hypotheses are good, so you can again keep only the best ones, and this way you continue until you find your winner, which is the best correspondences out of those, best hypothesis out of those generated. So I will now summarize. So I was speaking about non-uniform sampling that can speed up RANSAC significantly. I was speaking about two approaches. One was using assumption of locality, local density of inliers, and the other was assuming that you are able to sort or rank your correspondences and start first with better correspondences and then gradually go to I spoke about local optimization that stabilizes the results and reduces the number of samples, and combined with approximate models, this can bring orders of magnitude speed up. And then I spoke about degenerate configurations where you typically want to avoid wrong models with high number of inliers that are consistent with your degenerate configuration and some outliers. But this can be also used to efficiently detect models as degenerate configurations of some higher dimensional models. Then I spoke about checking samples for additional constraints, which can completely avoid verification by dropping models that are implausible. And these models are often seen in two-view geometry problems. Then I spoke about randomized verification, where you can significantly speed up problems with large number of correspondences. And again, most of those algorithms are implemented in USAC, which is a tool where there estimation of different models and different algorithms are implemented, and you can easily select those that you would like to use, and it's modular, and you can extend it or adjust it to the problem you are interested in. So thank you for your attention, and I'll be happy to go on the chat and try to answer your questions.